Hello, everyone. Let's start. So if you have any problem or question on how to install the Vivado, you can email me. In both the Canvas, I'll directly use my email address to email. So in this lecture, we will talk about truth table and the CMOS. Truth table is the logic you want to express, and the CMOS is the method, is the physical method you want to use to implement your logic. For example, here is a AND operation. So you want to perform a AND operation between two 1-bit input, A and B. And this is the truth table. Only when both inputs are 1, you get a output as a 1. Otherwise, the output are zeros. So this is the logic or the truth table you want to have. And then you can use this gate to implement the function of this truth table. And in this lecture, we will talk about how to use the transistor to implement this gate, particularly CMOS transistor. And sometimes you can have 3 inputs and gate, and then you also have a truth table. And of course, you can break this single 3 inputs AND gate into multiple 2 input AND gate. So this is the Boolean algebra to express this gate, and this is the truth table. Like we introduced in previous lectures, since there are 3 variables, 3 inputs, totally we have 2, 2, 3, 8 rows here. Only when all the inputs are ones, the output is 1. Otherwise, the output is a 0. When you have the Boolean algebra expression like an AND gate, OR gate, NOT gate, these are very simple examples. For more complex example, for example, you may want to, you may want to perform a neural network inference. These are all functions, logic functions, and you have different methods to implement these functions. For example, you can implement these functions by CMOS transistor or by FPGA. Luckily, previous work proposed some automatic method for you to achieve that goal, to implement those functions. This automatic method is a so-called synthesis. The process of synthesis is to construct a gate level abstract or gate level netlist from your VHDL code. And then this is so-called metadata. The gate level netlist is a so-called metadata. And you can do some simulation debugging to have some functional verification for these gate level netlist. Eventually, this gate level netlist will be synthesized further to CMOS gates or FPGA. But these are two major method to implement your function. Now I think even you can even synthesize your function to some quantum logic, which is not a CMOS gate or FPGA, some more advanced technology. So basically, you can use the existing tool, synthesis tool to do that. The modules builder and the logic optimizer are the existing tools. And these tools are, of course, included in the Vivado. By these tools, you can get the final area value, frequency value, performance data. And of course, if you use 45 nanometer to synthesize your function, you get a area and the performance value. But if you use more advanced technology node like a 10 nanometer to do the synthesis, you will have a better area value and higher frequency. But these are the, these parameters like area and the timing are technology specific. But when you do the programming by UVHDL, you don't need to consider that. You just implement your function like this. Today we will briefly introduce how to do the synthesis from UVHDL to FPGA and logic gates. So your function, like your 3 input AND gate, can be expressed by a truth table. Actually, all the functions can be expressed by a truth table. The FPGA is just some lookup table. So you can see these are lookup tables. These lookup tables are connected by some reconfigurable switches. These are the switches. You can directly store your truth table into the lookup table, so that when you do the computation, when you have A, B, C, your A is 1, B is a 0, C is a 1. You do the lookup by the key of 101, and then you have output. This is so-called a lookup table-based computation. For such simple truth table, I think one LRU or one small LRU array is good enough. But if you have a lot of variables here, which means that you will have a very large truth table, you need multiple LRUs in this case, and you need configure these switches to connect these LRU together. So basically, you can program these lookup table to store your truth table, and you can also configure your switch to connect your lookup table together. And in this slide, I will talk about how to convert the truth table to a Boolean equation or Boolean expression. We actually talked this issue before. The major method is to use the canonical form. So we can pick up all the output, the one output. So we can pick up all the rows which can generate a 1 in this truth table. And then we can write the so-called sum of the product canonical form here. For example, in this row, we can write A bar, B bar, because A and B are zeros, C, because C is 1, and D, So this is A bar, B bar, C, and D. And we can add these rows together. So eventually, after the simplification, we will have the Boolean algebra equation. And we will talk about the automatic algorithm for the simplification in the following lectures. So with this simple equation, we can use 3 gates to represent C. So in this way, we can convert this truth table to this gates. And we can set some intermediate variables to better understand the function of this circuit. For example, this X is A and B, Y is C and D, and then we add them together. So this is the Z. So in this way, we can, summarize the Boolean equation from the circuit. And then we can, draw a truth table to represent this equation. Because we have 4 variables here, so we have a 2 to 4, which is 16 rows here. And then we just list all the possible values for the A, B, C. And then we can calculate the value of Y and the value of Z. And eventually we can get the value of X and Y, and eventually we can get the value of Z. So in this way, we convert the circuit to a truth table. So we just do a 2-direction conversion between the circuit and its corresponding truth table. So basically, the circuit and the truth table are equivalent, so they are the same. And besides the FPGA, we introduced the FPGA which directly store the truth table. Besides the FPGA, we can also synthesize the truth table into some layout CMOS transistor. So this is the layout of the CMOS transistor. Because when we do the synthesis, when we do the layout level synthesis, we need to map your truth table to some gates. The gates have different technologies. For example, 10 nanometer, 45 nanometer. So you can see that the gates are different. After the synthesis, you need to do some so-called post-layout simulation. You want to verify if I use 10 nanometer technology, can these 10 nanometer gates can these gates achieve my design goal? My design goal is to operate my circuit at maybe 1 gigahertz. If I use and within some of course power budget, let's say 3 watts. If I use 10 nanometer to do that, probably yes, I can do that, because 10 nanometer has a smaller VDD, has a smaller power consumption. This can satisfy my design goal. If I use 65 nanometer to do the synthesis, maybe the power is too large, which means that they cannot meet my design goal. I have to redo the synthesis again. So when you consider the real gates, you need to do some post layout simulation, where you consider the effect, all the parameters of your gates, real gates, into the take these factors into the consideration of the simulation. But again, when we in the homework 1, we do some AND OR gate, and these are pure logic simulation. we have no gate at all. So the process technology or the gates or the fabrication or the physical gates matters. Here is one example. Apple company released a chip named A9 because of the manufacturer volume problem. They need to deliver a lot of mobile phones, so they need a lot of chips. But one single manufacturer, no matter it's a TSMC, a Taiwan company, or Samsung, a Korean company, single company cannot satisfy, cannot deliver such large volume of chip. So they have to, hire two companies that simultaneously, concurrently, to do the, fabrication. So they just hand out the same logic design, the same, truth table, the truth table of their chip, to these two companies. And these two companies, of course, have different real physical gates, different technology. And they will not share the technology because this is their advantages. Only this company can manufacture this gate. So by different technology, they basically achieve different chip area. So you can see that although you have the same design, but the chip area are totally different. And of course, the power consumption is totally different, which means that a part of the A9 chip can last a longer time, but the other chips may only stand for a shorter period or shorter latency. So we can see the real physical gate matters a lot. And when we consider the fabrication, there is a concept of yield. Yield means the percentage of your good chip out of the total chip. When you fabricate your chip on this die or this wafer, inevitably you may have some defects, and the defects may obey some normal distribution. So from this figure, you can see that if you have a very large chip area like this is your yield. If you have a smaller chip area, and this is your yield. So this is the reason why people prefer a smaller chip area, because a smaller chip area will give you a larger yield. Larger yield means you are paid this wafer anyway. Larger yield means higher, profit margin. With the same cost, you can sell more chips. And then on this, wafer, we have a lot of CMOS gates. And in this slide, I will talk about the CMOS gates. There are two types of transistor or gates. Transistor here is equivalent to gate. There are two types of transistors. One is a so-called NMOS. The other one is a so-called PMOS. You can consider the gate like a switch, as a switch. When I apply 1 here, so you can pass your signal through this gate. If I apply a 0 here, then you cannot pass the signal from through the gate. PMOS is just in the contrary case. if you apply a 1 here, you cannot pass the signal. This gate cannot let the signal go through this gate. If you apply a 0 here, the signal can go through this gate. So this is the real gate. You can consider that you can think about that the fact that we may have let's say billions of these gates in a single chip. So when we try to use this transistor to build some real circuits, we generally need this structure because the NMOS has good, has advantage to pass 0, but the PMOS has advantage to pass 1. So we typically, set the PMOS here, but we typically set the NMOS here in the pull-down network. PMOS are in the pull-up network. Pull-up network here is connected to VDD. These are VDD. VDD means 1. So this is why the PMOS, can pass better 1. Better 1 means it has a less noise. For example, if you have some signal, it can pass a very strong 1. This is a very strong one. But of course, the NMOS can also pass 1, but the 1 passed by NMOS may can have some like this. The signal quality may degrade. So that's the reason why we set all NMOS here in the pull-down network connected to ground, which is 0. And then you can have some input here. So these are the output. I will introduce more, give you more example about this pull-down network and pull-up network. For example, this is the simplest gate, NOT gate. So we just connect the control gate of a NMOS. This is NMOS and the PMOS together like this. So this connection here is represented by A. A is the input, Y is the output. So if I apply a 1 here, this one is enabled. Or you can say this NMOS is closed. Closed means this 0 can go through this gate to here. Since this is 1, this is closed, but this one is open. Open means when the switch is open, this 1 cannot go through this gate. So nothing can go through this gate. Only a 0 from here can go through this gate. So that's the reason why Y is a 0 now. So you can see this is a NOT gate. I give a 1 here, but I get a 0 here. On the contrary, if I give a 0 here, then this one is open. Open means nothing can go through this NMOS, but this one is closed. The PMOS is closed. So this 1 can go through this gate and reach the Y here, the Y point. So that's the reason why this is a 1. This is a 1. This Y is 1. So in this way, I give a 0, you get a 1. This is a NOT gate. So you can, use this table to do some analysis. Let's do another analysis on the NAND gate. Please recall that the so-called NAND gate is an universal gate. which means that by only this type of gate, we can represent any logic. So this is the truth table of the NAND gate. I will just, analyze what will happen if A is a 0, B is a 0. If A is a 0, this one is open. Open means nothing can pass through this gate. If B is open, this one gate is also is a 0. This one is also open. So this 0 cannot pass through this gate. But when A is 0, this one is this one is closed. When B is a 0, this one is closed. So both paths here can pass through the 1 to Y. So Y is 1. Yes, based on the truth table, Y is 1. We can continue to analyze a more complex example. So assume A is a 0, B is 1. What will happen? This one will open. Nothing can pass through this gate. This one is closed. Although this one is closed, 0 can pass through this gate, but when 0 reach here, nothing can pass through. So this 0 cannot go to the Y. This is a 0, so this one is also a 0. This one is closed. 1 can pass through this gate to Y. So here is 1, so this one is also open. Nothing can pass through this gate. So eventually Y is influenced by this P1. So Y is a 1. A is 0, B is 1, so Y is 1. Also, we get the truth table. We get the right answer of the truth table. You can continue to do the the analysis on A is 1, B is 0, and both A and B are 1s. So here is the algorithm for CMOS to build a CMOS network. So if I ask you to construct a function, this function, by CMOS gate, the first step is to invert the output. So we have a large bar here. When we do the inversion, we get this. And this equation will be implemented by the NMOS. Because we have a C all D here, the C all D will be converted to C and D in parallel. So they are in parallel. B in series B is a G1, so B is here. A parallel to G2, so A is here. So the step 2 is do the complement operations, which you can apply the De Morgan law here. And then you can use PMOS to implement everything here. So let me give you an example of the De Morgan law. After De Morgan law, this one will be this. B dot C D. So we have a B bar plus C bar and D. because we have a C bar here, D and a D bar. They are in sequential like this. This is all, so in parallel. This one is in parallel. And eventually, the whole thing will be in sequential with A. So this is the A. By two-step, we can design the first the pull-down network and then the pull-up network. So when we do the homework one, we do not need to consider anything about the gates. The gates are ideal, are perfect for us. But when you consider the real physical gates, you have to consider the resistance and the capacitance of the gates. These are important parameters which can generate heat, consume power, and introduce extra RC delay, extra latency. So the resistance of the gates is proportional to the length, transistor length, and the transistor width. That's the reason different process technology like 65 nanometer, 10 nanometer have different resistance and capacitance. And here is one example of the, how to calculate resistance of the transistor by this equation. And this slide introduced the capacitance. The transistor always have some parasitic capacitance. No matter how you optimize it, it always have some capacitance. With the capacitance and the resistance, it has RC delay. So when the input signal is something like this, the output signal may like this. When you change the input signal, you cannot get the output signal immediately change for you. It may have some delay. So this is the delay. The input signal changed from here, but until here, the output signal stayed the same. After this point, the output signal changes. So typically, we consider the delay as the time to go from 50% to 50% of the waveform. So when we design the circuit, we need to tolerate, we need to consider this latency. And this is the, NOT gate. We introduced this CMOS circuit NOT gate before. This is the ideal NOT gate. And this NOT gate can be, approximated by this equivalent circuit. And, two transistors will be equivalent to switch. These are the switches. And two transistors also have some parasitic resistance. These are the resistance. And the parasitic capacitance. These are the capacitance. So you can analyze the latency, the resistance, the capacitance by this equivalent circuit. Because of the current resistance, capacitance, the circuit will consume some power. There are two types of power that one circuit can need. The first one is a leakage power, which is static power. No matter you use that circuit or not, if you connect the current to that circuit, the circuit will consume this leakage power or static power. But when you try to do some computation by the circuit will consume extra power, which is a dynamic power. But only when the circuit is busy, you have a dynamic power. Otherwise, if the circuit is idle, there's no dynamic power. But no matter it's idle or busy, you are always paid the static power, the leakage power. So this is how the equation. This is the equation to compute the dynamic power. This is the equation to compute the static power. So you can see that actually when we compute the dynamic power, we have the frequency. So the frequency means you are busy. You do some computation. But you can see that the static power has no frequency at all. It's just that has VDD and I, which means that only if you connect it to the power source, you need to pay the static power. But the dynamic power is directly decided by the frequency here. Here is just one problem example. If I give you all these values, how to compute the power consumption. Again, the power consumption of a single computer system can be divided into two bars. The first one is dynamic power, the other one is static power. And you just plug these numbers into the equations. Eventually, you can get these values. And please notice that you need to unify the unit here. For example, this 1G is actually 1 multiplied 10 to 9 hertz. This NF, nano F is 20 multiplied 10 to minus 1. After you do the, you unify all the units here, you can get this value. Any question? So if you have any question, please email me. But in this lecture, we will not do the layout level synthesis. We just briefly introduce, the layout. We will focus on the logic design. So we will not have the real gates. If you have any questions, please email me, and you can email me in Canvas or by my email address. Otherwise, we can complete this class today. Thank you very much.
Thank you.
Thank you.
Thanks.